Okay, so my plan is to finish talking about the visual cortex today. That actually puts us a little bit behind because we need to get this information into a form of seeing objects and perceiving faces and moving that through the brain before we can actually talk about perceiving objects and scenes. Because again, we're here at these feature detectives. They are responding to features. They are responding to different orientations of lines in the environment and direction of movement, and then maybe how long that line is and the angle and so forth. And so then we start talking about the organization or mapping of this primary visual cortex, of the striate cortex. So how are the neurons organized? And we gave it's a retinotopic map. It has the same kind of mapping of what we see on the retina. And we have foveal magnification. So it's we're seeing there's larger area of the cortex responding to the fovea than to that peripheral information. But so far, what we're looking at is the surface of the cortex. And we also want to look below the surface. So I don't remember if I've said it in this class, but throughout our cerebral cortex, yes, because I talked about the lateral geniculate nucleus, and that it has those 6 layers, and that we looked at particular columns, right? Well, we see a similar kind of 6 layers here in the cortex, and we want to look within the columns. So we want to go perpendicular to the surface, and what we see are location columns, orientation columns, and ocular dominance columns. So when they put an electrode in and it's going perpendicular to the surface of the cortex, all of the neurons within a particular location in the cortex have their receptive fields at the same location on the retina. So they're really representing a particular location in space. And I usually do this thing of standing up in front of the class and just kind of putting up a pen or my finger or something and saying, if this is on your right side, then you have a particular area in the left visual cortex that is responding to this particular location. And I'm going to continue on with that example. We also have orientation columns. So neurons along one of these specific tracks also prefer stimuli with the same orientations. And what this is showing is, what the picture is showing is, well, the cortex is curved, because remember we have those gyri and sulci, and we have these curves so that we have more surface area to our cerebral cortex. And if we're going in at the surface of the cortex at A, and we put in our electrode, then everywhere along in that column, when we're measuring at A, it's going to be responding to a horizontal line. And if we look at B, so we move out a little bit at B and move along, go down in a column from the surface of the cortex, and every single neuron in that column is responding to a particular location in space and responding to a particular orientation. So it only is going to respond when, I'm going to pretend that's kind of vertical, even though it looks a little bit oblique to me, but it's going to respond to the vertical line. So here I am, I have my finger up, it's in your right visual field, it's hitting the left sides of your retinas, going back to the left lateral geniculate nucleus, going back to the cortex, and there's an area of that cortex in the left hemisphere that is responding to that location and the fact that this is a vertical line. So that particular column is where you're going to see neural firing. And the last kind of column that I'm going to talk about at all is the ocular dominance columns. So again, going perpendicular to the surface of the cortex. If we go in, we see, well, first of all, we see that 80% of neurons really respond to stimulation of both the left and right eyes, but most of our neurons respond better to one eye or the other. So we have these neurons that have an ocular dominance. And again, we're going to see these location and orientation columns, but also with a left eye dominant, right eye dominant neuron, if that makes sense. So these neurons with the same ocular dominance are also organized into columns. Discussing the visual cortex, when we started talking about those feature detectors, this is a reiteration of those simple cells, complex cells, and end-stop cells that Hubel and Wiesel discovered. I went through and gave examples of each, so hopefully they make sense that we have particular neurons that are responding to particular orientations of lines or bars out in the environment. We have other neurons, the complex cells, that are responding to a particular orientation of line with a particular direction of movement. And then we have end-stop cells that respond to really the length, angle, orientation, and direction of movement. And how does this look? They actually have a really neat picture. I don't know if it's still in the book, and I used to have it in my slides, and I can't seem to find it now, where they don't look like these hypercolumns. They are not these perfect cubes, okay? But they're because the cortex is curved and has those folds, they are sometimes kind of wrapped around. But nevertheless, when we go in perpendicular, we see hypercolumns. So hypercolumns that include are giving us information about a particular location. They have these orientation columns. So what you can see going from kind of right to left we're kind of on a z-axis is where I'm putting that. We start with a vertical and then these different obliques until we get to horizontal. So we have these different orientation columns. And if you see the R and the L there, within the location column, we have a right eye dominant column and a left eye dominant column. And I'm going to ignore that we also have these spatial frequency columns in there as well that are columns that are responding to either close spatial frequencies, things that are really busy and the lines are close together, versus more spread out lower spatial frequencies. I'm going to ignore those because your book ignores those. So this is kind of the idealized column, hypercolumn, looking at it as this cubicle kind of thing, but it's really kind of wrapped around and warped with the folding of the cerebral cortex. We want to get to this question of how is an object represented in the primary visual cortex in V1 or the striate cortex. How does this electrical activity stand for or represent the object in the environment? So we have, in this example, a person is looking at a tree. We have that image hitting the retina. The photoreceptors are firing. The retinal ganglion cells are receiving their information. They're sending it on to the brain, to the lateral geniculate, to the visual cortex. We have this representation in the striate cortex that is similar to the image on the retina that, remember, has already gone through a process of transformation and representation, but now we have more space that is devoted to the fixation point or the fovea as well. And of course, it's pulled apart into these hypercolumns, where a particular hypercolumn is going to give me vertical bar, horizontal bar. What kind of feature am I looking at? Is it right eye, left eye, dominant, and so on within that? So if we're asking the question, how is an object represented in the visual cortex or in V1? Okay, so we're looking at the tree trunk, and we're seeing activity in a number of separated orientation columns. They are giving us each location, and those locations are close to each other on the retina, but these orientation columns, A, B, and C, responding to those areas of the trunk A, B, and C, are now separated in the visual cortex. So this looks quite a bit different than the stimulus itself anymore, and it becomes really clear that cortical representation is not resembling the stimulus, it's representing the stimulus. And the representation of the trunk of the tree in the visual cortex is really, again, just the first step, because we need to process this information and recognize it as the trunk of a tree, and that it's related to this bushy tree, these leaves and everything that's on the top. This information is going to go to a number of other places for higher level processing, so that we can understand what objects are in our environment and where those objects are in relation to ourselves and to other objects. So I'm going to come to this mind-body problem that I typically do right after talking about physiology and then come back to a couple of times. I'm realizing that we're pretty behind, or I was trying to put that review of concepts so that we've gone over this problem and maybe even come to it a couple times, but we're going to review some concepts on Monday where you all are going to explain them to each other, and there's going to be at least one kind of more philosophical group that is going to be addressing the mind-body problem. So if you're really interested in this question and this problem, and you're watching this on Friday, you might email me and let me know, hey, I want to be in this group. Otherwise, I'm going to randomly place you all into groups. But so the mind-body problem is really the question of how does the mind and thought and perception and all of that relate to the body and the brain and the real physical aspects of our mental lives. So how do these physical properties like nerve impulses or what made up of, right, sodium ions and potassium ions flowing across a membrane, how do they transform into the richness of perceptual experience? I'm going to walk through this in a number of ways, and I really want you to think about the question and think about right now in the visual cortex, are we there? And again, I feel like I'm a little bit early, I guess, with this review of concepts because we're behind, but we're going to come back to this when we really start to put the information back together. We've really pulled it apart into features, and we want to put it back together into what those features make up, right? So my table over here, or somebody's face, or the television set, or whatever. But this mind-body problem is really often referred to as the hard problem of consciousness, coming from David Chalmers. There's an easy problem of consciousness, which is how do these physiological responses correlate with experience? And most of the research, it's really looking at correlations. We're looking at what are people perceiving, and then we're measuring their brain activity, and that's really the gold star of that kind of triad of whether I get a psychophysical measure, a physiological 1, or a physiological 2. I want the physiological 2, right? I want to put up the stimulus, let them tell me what their perception is, and get a measure of brain activity. But even with all of that, we're looking at correlations of here's the brain response, the physiological response with that correlates with this particular experience. The hard problem of consciousness is how do these physiological experiences or these physiological responses cause experience or transform into and become our experience of the world? And I have some examples here. So how do neural impulses become the perception of a person's face, the experience of the color red, or the feeling of a bitter cold wind? And every one of those things we can think of, there are emotional responses, right, to a person's face. There are thoughts of, is this somebody I'm working with? What are we working on? All of that comes into our mind suddenly because we look at a certain person's face. Some people in my class do this kind of, what kind of emotion does the color red cause, right? Is it an attraction kind of thing? Is there a withdrawal because of stop signs kind of thing? Do you want to wear the color red? Questions like that. And this experience of the color red, while we're not even sure we're really experiencing the same thing, we're just pointing to the same thing and calling it red, what we have is the measurement of neural impulses. And I usually use the example of that we'll get back to in olfaction. And I don't come back to the question, but you might kind of write it down somewhere so you're thinking about it. But when my mom makes sticky buns, so if your mother makes, or somebody, or you make monkey bread, I think it has a similar smell probably to sticky buns. Sticky buns, you make this kind of cinnamony, buttery, sugary, so it's moist, and then you take the dough and you roll it, you smear the moist cinnamony sugary stuff onto the dough, and then you roll it up and bake it. And every time I smell that smell, I'm just transformed. I just go back into my grandmother's house and I can see her. I can see her beating on she used to make her own bread dough and make a whole bunch of them, and they'd be all around the house. And my grandfather, I can picture what room he's in and the room that we played in, and coming home from school and all of that. And I didn't live near my grandparents. I lived with them for a really short time. My grandmother died in 1983. So this smell can bring me back so in such a vivid way that it's incredible to me that it's actually just the flowing of potassium and sodium ions and releasing some neurotransmitters that is causing this experience. And so I hope that you have a similar kind of, wow, how do these physiological responses, how does brain chemistry and ions flowing cause or transform into experience? And if I go back to it here, I'm asking the same question again, only if you remember where we are right now is in the visual cortex, and we are looking at a tree, and we have the representation of this tree as these separated orientation columns that's the little area that is responding to a vertical orientation. They're separated by location, but because of the way hypercolumns are, they have this separation in space in the brain. And I want to ask the question, and I think I went through it pretty well on the last slide, but are we addressing so far the easy problem of consciousness, this question of correlation, or are we addressing the hard problem of consciousness, how physiological responses become the perception of a tree? Okay, this is a really good place to stop, and if I go on into different kinds of coding, I think I'm going to save that for after we put some of this information back together. So we are a little bit behind, but I do want you to think about these questions, and I'm hoping people are listening, so Friday and Saturday, I'm going to put you into groups, give you a concept, email you that concept in basically a sheet or two of explanation, and then you within those groups on Monday, you're going to have about 20-25 minutes, probably more like 22 minutes, to get together, discuss the concepts, and decide how to explain it to the class. And usually the way I do this is with crafts in class, but this is the first time I'm not able to do this with you in person. So I'm just hoping it all works out on Blackboard Collaborate. But if you can think of any way to, over the weekend, if you look at things, again, when I email them, I'll send a little bit of this again. But I know different people see and hear things differently depending on where they get it. So if you have a neat way to communicate or something you can create that can help communicate any of this, when you share it on Blackboard Collaborate Ultra, it'll have to be in the form of, okay, a PDF. It says an image, so I don't know if it takes JPEGs and other images, but an image or a PowerPoint. So somehow you can get an image into a PowerPoint or a JPEG file. You can put up a PDF with some explanation with words. However we get through these concepts, I usually think it's a really good time to review before we move on into putting this all back together, really into the psychological processes like perceiving objects and scenes, and certainly before this first exam comes up. Okay, think about questions. Although Monday I'm going to have you all explain things. But if you have a question, ask it.